In this presentation, I'd like to discuss some of the work we've been doing on neuromorphic computing in the Silicon Photonics platform. Now, most of the time, we've been using a paradigm called reservoir computing. Now, for those of you that are not familiar with reservoir computing, a very quick introduction. Now, reservoir computing is obviously something from the field of machine learning. It was proposed almost 20 years ago now, and it was originally introduced as a way to solve problems that people had at the time when they were trying to train recurrent neural networks. So it's some sort of shortcut to make your life easier there. And it turned out to have quite some good performance in many different applications: time series prediction, speech recognition, robot control, and very specifically in situations where there's lots of noise in your input. So it turns out to be a very robust method of dealing with noisy input data. Obviously, originally it was introduced as a purely software technology, but what we've been doing is taking this paradigm and implementing it in silicon photonics. Now, how does it actually work? Well, the idea is the following. You have a recurrent neural network, which turns out to be quite difficult to train. And if the observation is that this recurrent neural network, with all of its feedback loops here, is so difficult to train, we're simply not going to train it at all. We're just going to randomly initialize it. And then the only thing that we are training is this separate linear readout layer that comes after that. So we're just making linear combinations of the different time traces of everything which is happening at all of the nodes inside our reservoir, inside our recurrent neural network. And then by optimizing the weights of this linear combination, we can train the system to perform a useful task. This is the principle behind reservoir computing. Now, this seems a bit strange because what we're doing is we're coming in with some sort of time signal that we're trying to operate upon. And then we're making this even more complicated by sending these time signals through this very complicated nonlinear dynamical system. And then I'm telling you that by taking simple linear combinations, you can do useful stuff with it. So how does this work? What's the reason for this? Well, it's well known in machine learning that there's a certain problem called overfitting. If you have a certain data set, like for example here, relationship between house size and price, if you have this data set and you want to fit a certain model to it, for example, in this case, a 6-degree polynomial, then you can basically see that you're able to fit all of your training data exactly with zero error. But then you have a model which is very poor in generalizing to data which it hasn't seen before. So it's much more advantageous to take a much more simple model like this model, which will perhaps not go through all of the data points exactly, but which will be able to generalize much better in the presence of noise and measurement data and measurements error. Now, that's exactly what reservoir computing does. It takes your data, moves it through the reservoir into a much higher dimensional space, such that you can get away with a very simple boundary between two different classes, namely this linear combination which gives rise to a hyperplane. So if you have data which is non-linearly separable in a lower dimensional space, thanks to the reservoir, you move this into a much higher dimensional space, where then class elements belonging to the same class will still cluster together. But now, since there's so much more space in this higher dimensional space, you can basically get away with just using a simple hyperplane to separate these two classes. And that turns out to be much more robust against noise, measurements, errors. So it's a much more robust technique to perform classification. So this is in a nutshell what reservoir computing does. Just as an illustration, people have actually performed a hardware implementation of reservoir computing in a lowly bucket of water, where the reservoir is just the nonlinear system formed by the surface of your water inside the bucket. And then if you throw in certain objects in this bucket, either pebbles or grit, you can easily understand that depending on what you throw in, you will set up different wave patterns inside this bucket. And then by observing these wave patterns and taking linear combinations of pixels, you can answer questions like, what did I throw in, pebbles or grit? How many pebbles? How long ago? So these types of things. Obviously, what we want to do is not play around with buckets of water, but rather implement this in photonics. And this is the first hardware implementation on a silicon photonic chip of such a reservoir that we tried. And it's, of course, silicon photonics is very attractive, very mature technology. And the structure of the reservoir is also quite simple. It's basically a giant multipath interferometer. So you come in with your input signal here on this particular node, and then you have this network consisting of all sorts of splitters and combiners, giving rise to feedback loops, such that if you measure a certain output, there are many different paths between the input and that output, which will all interfere in a very complicated manner when you measure the intensity at the output. So in the complex domain, this is a purely linear system. The nonlinearity that we need actually comes from simply detecting the signals at the output with a photodiode. So you come in with a complex valued electric field, and then what you measure is a real valued intensity, and that nonlinear operation turns out to be more than enough for a large number of applications. So it's a very simple system which does not need any active component inside, which is also very easy from a technological point of view. It's also quite easy to scale this up to higher speeds because the time scale here is set by the propagation delay between, for example, two nodes here, which is set by this spiral, by this delay here. Now this delay is simply there so that the dynamics are compatible with our measurement equipment. If you were to get rid of these delay lines, this whole chip would run at hundreds of gigabaud per second. So it's a technology which is very easy to upscale to much higher speeds. In many technologies, it's the other way around. You have to work very hard to speed it up. Here we had to perform some efforts by introducing these spirals to slow down our system. And again, there's no active component, very easy technology. And exactly the same generic chip can be used both for digital tasks and for analog tasks. So some digital tasks that we've been doing with this as benchmarks are just Boolean logic, header recognition, analog tasks, for example, speech recognition, or more relevant, dispersion compensation in telecommunication links, but more about that later. So it's a very simple generic architecture that can be used to tackle a large variety of applications. Speaking of applications, let's move to a little bit more detail on the topic of nonlinear dispersion compensation, which are some experiments that we did to try and solve the following problem. Now, obviously, you know that if you send data through an optical fiber, then there's all sorts of distortion, linear and nonlinear dispersion that can happen, such that the eye diagram at the output is basically this huge mess here. You can fix this, of course, using DSP, but especially for coherent modulation formats, this DSP can be quite expensive and extensive. So wouldn't it be nice if we had some sort of way to do this dispersion compensation in the analog optical domain so that we can offload some of the calculations from the electronic DSP to the optical domain? So the idea here is to train the reservoir such that it undoes the nonlinear dispersion that happens inside the fiber, cleaning up the eye diagram such that you have much better separation between the decision boundaries. So these are some simulation results, but we've actually experimentally realized this using a silicon photonics chip. And these are the experiments that we did. So we have a bit stream that we send through an optical fiber. And before that optical fiber, we have this amplifier here, such that we make sure that we really hit the nonlinear regime of the optical fiber. And then at the output, we normalize the power levels, and then we detect this with a simple photodiode. Now, then we try, as a matter of comparison, to do linear dispersion compensation by having a tapped filter there. And we also try to do a second experiment by having nonlinear dispersion compensation with a reservoir. So in this particular setup, we introduce this extra component, this extra reservoir chip here in front of our detector. And then from each of the nodes inside this reservoir chip, we basically record a time trace like this. And then we train the system to take a certain linear combination of these time traces such that we can recover much clearer output signals. So if you do this, these are the results. These are different eye diagrams. The one on the left is if you don't do anything at all. So this is just the raw output of the optical fiber. And the bit error rate is not so great, obviously, 10 to the minus 2. If you try and use a simple tapped filter, either in the electrical domain or in the optical domain, then you can do a little bit better. The performance increases by roughly 1 order of magnitude. But if you do use reservoir computing, which can also undo nonlinear dispersion, then you can clearly see that the eye opens up considerably. And basically, you do not get any error at all in the roughly 10 to the 5th bits that we send through this system, which then statistically translates into a bit error rate, which is a lot lower than 10 to the minus 3, but we do not know at this stage how low it actually is. Just for 10 to the 5th bits, we do not have any error. So this thing just clearly experimentally shows that we can do nonlinear dispersion compensation with this reservoir chip. I'm obviously not saying that you cannot get similar performance with electronic DSP, but the nice thing here is that you can do it entirely in the optical domain without needing complicated DSP here. It turns out that we can do even better for systems like these if you make use of the nonlinearity in the photodiode even more. So rather than having an ideal photodiode, you add some extra nonlinearity in its transfer characteristic, and by then exploiting that and taking that into account in the training as well, you can basically gain also a couple of more orders of magnitude in performance here. But these are actually simulation results. These were all results for on-off keying. Obviously, nowadays what people want is more coherent modulation formats, like for example this QAM constellation, where you also have amplitude and phase at the same time carrying information. But then, of course, the disadvantage is that you need a coherent detector at the receiver, which is a much more complicated system, requires local oscillators. So the cost there is obviously, in many cases, quite high if you have short lengths. Now, this is why people a couple of years ago introduced a different type of receiver scheme based on the Kramers-Kronig dispersion relationships. And basically, the idea here is that for a certain class of signals, you can get away with just measuring the amplitude of the signal, and then by doing some DSP, you can extract the phase information as well. Now, obviously, this is not true for all signals. What you need, for example, is a situation where you have this subcarrier here to the left or to the right of your data stream, and you also need to make sure, in a second condition, that that subcarrier has enough power. Here you see an example of a constellation reconstruction of a Kramers-Kronig receiver for different values of that power in the carrier. So for low powers, the reconstruction is not good, but if the power keeps on increasing, then you see that the performance of the reconstruction becomes very good. So this is an essential ingredient of the Kramers-Kronig receiver, which basically makes that your signals are minimum phase. Now, how do you make sure that that subcarrier has enough power? Either you add that subcarrier at the detector. This is what most people do nowadays, but then the disadvantage is that you need another local oscillator at your detector side. Or you can also add it at the source side. But then you have the disadvantage that you inject at high power also in the optical fiber, and that gives rise to lots of nonlinearities. But we've just seen that reservoir computing can deal with these nonlinearities in a very straightforward way, basically in the analog optical domain. So the question here is, can we use this simplified and much more attractive version of the KK receiver, where you have your subcarrier injected at the source side, and then use the reservoir to clean up all the nonlinearities that you suffer from? And these nonlinearities are quite high. This is a simulation of what happens if you have, for example, these 4 constellation points here. At the output of the fiber, it's basically a giant mess. Now, again, we're trying to train the reservoir to undo all of these dispersion effects, and specifically nonlinear dispersion effects that can happen. But here it's a little bit more complicated because we do not have a simple detection here. Rather, we detect the signal and then we send it through the KK receiver, which performs all sorts of DSP in a highly nonlinear way. There's logarithms involved there. And what we're actually doing is we're not just doing classical reservoir computing in the sense that we, for example, assume that we know what the signal is here just after the detector. No, what we're doing is we're taking the entire KK receiver pipeline into account to optimize the weights of that linear combination here. In terms of training, this is a bit more complicated because we do actually need to do a backpropagation through all of the operations in the KK receiver. But it turns out that if you do that, you can really exploit these extra nonlinearities again and get a performance which is much, much better. These are the results. And on the left, we have a comparison with a simple linear equalizer. In this case, a tapped optical filter again, 16 taps. And on the right-hand side, we have the reservoir computer or the linear, linear in the optical domain, but non-linear as once you add the KK receiver. So this reservoir equalizer here also can undo the non-linear effects, and the bit error rate basically reduces 2 orders of magnitude. These are all simulation results, by the way, but the next step is trying to implement this in a hardware experiment. We've also been using techniques like these to tackle other telecom tasks. So just to give you a flavor for what else we can do with reservoir computing, this is a simulation of exploiting the wavelength dimension in telecommunication signals. So here we're doing a binary task, like calculating the XOR of the current bit with the previous bit in your data stream. But we optimize the system in such a way during training that it can perform this task simultaneously on a number of WDM channels. This is an example of 2, but we can also do many more. And the important part here is that all of these wavelength channels can get sent through the same readout system with the same weights for all of them. So you could have a weighting in the optical domain on chip and have it operate in parallel on all of these WDM channels. So this basically boosts the throughput of your system considerably. By playing around with these different training schemes, you can also make your system more robust against, for example, wavelength drift of your source laser. If you just train your system to operate at a single wavelength over here, then you basically get a 3 gigahertz window in terms of wavelength drift of your laser. But if during training you also want your system to work very well at other wavelengths, for example, you also include these 2 wavelengths over here, then all of a sudden now you get a much more robust system where the bit error rate is basically very low for a 8 gigahertz window in this case. So this is a very simple trick to make your system more robust, simply by during training having it exposed to much more environmental changes in your system, either wavelength drift or temperature, and that way you can get a very robust system. We've also been using reservoirs to, for example, identify if people are trying to jam your precious telecommunication signal, either in-band jamming like over there or out-of-band jamming over here. And the nice thing is that we can basically identify this already after a couple of periods. So it's a very fast real-time scheme without the need to gather lots of information and then post-process that offline, as what is happening typically in these types of jamming detection systems. We've also been training reservoirs to identify modulation formats, like for example trying to figure out if you have BPSK or QPSK on your link, and then depending on different architectures with different nonlinear components, you basically get either very good performance or not so good performance. So this is just to illustrate that you can get many different types of applications in systems like these. Finally, I want to talk about a completely different type of application, which is more in the biological field, which is inspired by a cell sorting problem. Now, in order to figure out if certain cells, biological cells, are cancer cells or not, what people typically do is they send these cells one by one through a very thin capillary tube in a system called a flow cytometer, and then they excite it with a laser, and then they try and figure out by looking, for example, at the morphology or at the fluorescence of these cells, whether this is a cancer cell or not. Now, some of our colleagues at IMEC have been trying to develop a system like this on a chip, where they basically want a flow cytometry system with thousands of channels in parallel on a single chip. And you also want this thing to operate label-free, so without any fluorescence here. So you just have a mixture of populations of cells that you send through this channel. And then here you're trying to image what's happening to these cells as they flow through this channel by basically exciting it with laser lights and then recording a hologram over here. So just the interference of the directly transmitted laser light with the laser light which is scattered by the cell. So you record a hologram here on some sort of imager system. So this is lens-free digital holography. And then you want to process that hologram very quickly to try and figure out if this is a cancer cell or not. You basically have enough time to do your calculation, and the time is set by the propagation of the cell through the channel. So once your cell arrives here, your analysis system should have determined whether this is a cancer cell or not. And then here you generate a small puff of steam to either send the cell through one channel or through another channel. Now, if you want this for 1,000 microfluidic channels in parallel, you basically need a supercomputer to do this in the traditional way. And our question here was, can we use some sort of photonic processing in the analog optical domain to speed up this problem? Now, one thing where we can obviously win is that what's typically happening here traditionally is you have this hologram, and then you try to solve Maxwell's equations in reverse to try and get a real space image of your cell, and then do classical image recognition on that cell. But this is quite time consuming. What we're trying to do is we're going to operate directly on the hologram and see if there's information on the hologram to help us determine whether we have cancer cells with a very thin nucleus or regular cells with a different size nucleus. So this is the problem that we're trying to solve. The way we're doing this is again inspired by reservoir computing. We're going to get our hologram here and have it propagate through these layers of different scatterers. So the light will propagate back and forth between all of these scatterers. And then at the end, when it gets measured by your camera, it will have had lots of different interference going on. And then you record all of these nonlinear interference patterns. And then you do a linear classification of the different pixel values. So the idea of this spatial reservoir, if you want, is to try and increase the information content that is present in your image here, in your hologram, such that with a very simple linear classifier, you can answer the problem like what type of cell is this. And indeed, it's very clearly obviously from the simulations that these scatterers increase the information content. If you have no scatterers, your image looks something like this. If you have periodic scatterers, there's already more information content. But if you have these randomized scatterers, you see that you have a very rich pattern here, which contains much more information to classify these signals. We've also been doing this experimentally. So these are some holograms that we measured, either without scatterers or with scatterers. And then we just took linear combinations of certain pixels to try and identify, in this case, beads with different sizes as a stand-in for these cancer cells versus non-cancer cells. And then we did an analysis to see whether we could do this quickly or not. And these are the results compared to other results from literature. What you see here, if you look at the classification performance, that it's roughly in the same order of magnitude. But the important part here is that since we have a very simple linear classifier in the electronic domain, just linear combinations of pixels, and most of the heavy lifting is done in the optical domain by these interference patterns, we can get quite good speed, quite good performance here. If you look at the time it takes us to do an analysis compared to what other people have been doing, then you basically see that from the millisecond range, we can easily get to the sub-millisecond and sub-tenths of millisecond range, even in a system which does not have GPU acceleration. So with this reservoir computer-inspired approach, we get very fast classification of different types of nanoparticles. Next steps here is trying to repeat the same experiments, but with an event camera, where we do not have to do other calculation steps like background subtraction. So these are experiments which are ongoing now to get even better performance and even higher speeds. So to wrap up, looking at all of these different examples that I've been showing you, I hope I've convinced you that reservoir computing is actually quite an interesting paradigm for information processing in the analog photonical domain.